Hello guys, in this video we are going to continue with the beta function. The objective is to understand and apply this beta function in trigonometric integrals. We have seen these beta functions for another type of integrals, but in this video we are going to focus on trigonometric integrals. For sure, it's only for a specific type of trigonometric integrals. Okay, we will understand the connection between beta function and the integrals of this form. You will see in no time. What are we going to need? Okay, we are going to need, as usual, a little bit of calculus, a little bit of trigonometric identities, and the gamma function. That is very important because beta function is closely related with gamma function. So if you don't understand how to apply or how to calculate gamma function, then this video has no use. Okay, let's continue. The beta function that we have seen, it's depending on two parameters, p and q, and is defined as the integral between 0 and 1 of t, the variable, power to p minus 1, 1 minus t, power to q minus 1. Okay, this is the specific shape of a beta function. For p and q, positive. Remember that p and q could be rational numbers. For sure, it should be positive, but you don't need to have natural numbers, okay? They can be fractions. Okay, so applying a change of variables, in fact, this change of variables you see on the screen, t equals sine square of x, this transforms this integral into a new type of integral. It's exactly the same formula, it's exactly the same, but it transforms something that has no trigonometric functions into something that has trigonometric functions. Be careful because the shape is exactly what you see on the screen. If anything changes, be careful because probably you cannot apply this formula. Okay? So we have that beta, the function beta at pq, it's 2 times the integral between 0 and pi half of sine of 2p minus 1 cosine of 2q minus 1. The problem in these integrals is not the shape. You are going to recognize the shape. Be careful with the interval of integration between 0 and pi divided by 2 and the 2 multiplying the integral. But the problem at the end is you will see here a number, you will see here a number, and the only important thing is that you need to know which is the value for p and which is the value for q. Okay? I hope you understand in the following examples. Remember these two, okay? The beta function pq is 2 times this integral. Therefore, you can rewrite this formula as follows. The integral between 0 and pi divided by 2 of sine 2p minus 1 cosine 2q minus 1 of x at x dx, it's 1/2 of the beta function pq. And now it's when the relation with the gamma function comes into play. The beta pq is exactly gamma p times gamma q divided by gamma p plus q. Okay? And you need to remember how to calculate these values. What is gamma p, gamma q, okay? We will see in a few moments how to do that, but anyway, you need to review this part if you don't understand what gamma p means, okay? Let's see an example. By the way, this is worth the effort, this method, because it's going to simplify integrals that otherwise are going to be really, really difficult, okay? For example, the integral between 0 and pi half of sine cubed cosine to the 5th power. This integral can be solved using changes of variable. In fact, this trigonometric function is odd in sine and odd in cosine. So there are many changes, 2 changes of variable to solve this integral. Anyway, these changes will lead to a more difficult exercise, more than the one we are going to apply here right now. Okay, so the idea is, okay, this integral has the shape of the previous formula. Remember that the previous formula was like this, okay? So in this case, the only thing that I need to find out is what is the value for p and q. So if 3 is 2p minus 1, then for sure you can solve this easily. P is equal to 2. And if 5 equals 2q minus 1, it's easily seen that q is just 3. You only need to solve. So p and q are known. P is 2 and q is 3. So this integral can be written as 1/2 of gamma 2, gamma 3, and gamma 2 plus 3. Gamma 2, The gamma is the generalization of the factorial function. So, gamma, but one number one unit less. When you are calculating gamma of 2 or gamma at 2 is just 1 factorial. Gamma at 3 it's 2 factorial. Gamma at 5 is 4 factorial. Then you only need to simplify things to obtain 1 over 24. Okay, it's not difficult. Come on, another example. Sine squared, cosine squared. The same shape, the same form. The only thing you need to know is P and Q. What is the value for P? Okay, if this exponent is 2, should be 2P minus 1, then it's easily obtained that P equals 3 divided by 2. Okay, and if this 2 should be 2Q minus 1, is easily observed that Q is 3 divided by 2. So this integral is 1/2, using the formula, 1/2 of gamma at 3 divided by 2 times gamma at 3 divided by 2 divided by gamma at 3 divided by 2 plus 3 divided by 2. By the way, this is 6 divided by 2. This is gamma at 3, okay, on the denominator. Remember that gamma at 3 divided by 2 is 1/2 times gamma at 1/2. And gamma at 1/2 is square root of pi. So I am using properties of gamma function. It's very easy, but again, if you don't remember how to calculate gamma function, go back to the video of gamma functions and review it, because it's very simple. Okay, so gamma at 3/2 is it's 1/2 times square root of pi. Gamma at 3/2 is 1/2 times square root of pi, divided by, remember, this is gamma at 3, so 2 factorial. Then if you simplify square root of pi, it's pi only, and 1/2 is just 1 over 4, 1 over 8, and 1 over 16. That is the result we obtained here. You can just simplify and obtain this result. Okay, so this beta function simplifies the resolution of integrals of a specific type. Be careful, because the limits of integration are from 0 till pi/2, and if something changes, be careful. Probably you can apply a change of variable in order to rearrange the integral and obtain the beta function, but it's going to be a little bit more complicated. I hope at least that you understand how to apply the beta function. That is one of the key takeaways that I want you to have in this video. And also apply this in specific examples and be able to solve this kind of integrals. Okay, guys, thank you for your attention.